One of the most profound things about being alive in this universe is that you don't have to understand quantum mechanics to know that something fundamental is missing from our picture of reality. You feel gravity every single second of your existence. Right now, as you sit there watching this video, you're being pulled toward the center of the Earth with a force that is constant, relentless, and utterly invisible. But here's the thing that absolutely haunts physicists. We don't actually know what gravity is. Not really. We have equations that describe how it behaves. We have theories that predict its effects with astonishing precision. But what gravity actually is, at the most fundamental level, remains one of the deepest mysteries in all of science. I'm Neil deGrasse Tyson, and I've spent decades looking up at the cosmos, trying to understand our place in this vast universe. And the more I've learned about physics, the more I've realized that gravity, this seemingly simple force that keeps us grounded, that keeps the moon orbiting Earth, that keeps the Earth orbiting the sun, that holds together entire galaxies, might be the most mysterious phenomenon in all of science. It's the invisible hand that shapes the cosmos. It's the architect of galaxies. It's the sculptor of stars. And we're only just beginning to understand how little we actually know about it. Today, I want to take you on a journey through one of the deepest mysteries in physics. We're going to explore what gravity really is, where it comes from, how it works at the smallest and largest scales of the universe, and most importantly, we're going to examine how understanding gravity might fundamentally break our current understanding of the universe and force us to rebuild physics from the ground up. This is not a simple story. It's a story full of contradictions, mysteries, and questions that have haunted the greatest minds of our time. When Isaac Newton formulated his law of universal gravitation in 1687, he did something truly remarkable. He took observations of falling apples, planetary motions, tides, and the orbits of celestial bodies, and he unified them all under one mathematical principle. His law states that every mass in the universe attracts every other mass with a force that is proportional to the product of their masses and inversely proportional to the square of the distance between them. In mathematical form, it's elegant. In practical application, it's powerful. For more than 2 centuries, it worked beautifully. Scientists used Newton's mathematics to predict planetary positions with astonishing accuracy. They calculated the trajectories of comets. They determined the orbits of moons. They understood the dance of binary stars spiraling toward each other in the cosmic dark. Newton's theory of gravity was so successful that it became the foundation of classical mechanics. It allowed us to understand the motions of the heavens and the earth. It made possible the age of celestial mechanics. And yet, Newton himself admitted something remarkable. He had no idea how gravity actually works. He wrote, and I'm paraphrasing here, "It is inconceivable that inanimate brute matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact." In other words, Newton looked at his own equations and basically said, "I have no idea how the Earth reaches out across empty space and pulls on you. I just know that it does." This admission from one of the greatest minds in history reveals something profound. Even genius has its limits when confronted with the deepest mysteries of nature. That unsolved mystery haunted physicists for centuries. How does gravity propagate through empty space? What is the mechanism? How can 2 objects separated by the vast vacuum of space exert forces on each other without anything connecting them? These questions seemed almost metaphysical. They seemed to violate the principle that something cannot act where it is not. And yet, gravity clearly does act across empty space. The sun's gravity reaches across 93 million miles of empty space to hold the Earth in orbit. And billions of years ago, when the sun was born, it wasn't close to the Earth. It was a collapsing cloud of gas and dust. Gravity acted across that entire cloud, pulling it together, concentrating it, heating it, until nuclear fusion ignited in its core. Then, in 1915, Albert Einstein revolutionized our understanding of gravity with his theory of general relativity. And instead of thinking of gravity as a force, Newton's invisible hand pulling objects together, Einstein showed us something far more profound and far more strange. He showed us that gravity is not a force at all. It's geometry. It's the shape of spacetime itself. Imagine spacetime as a rubber sheet stretched out in all directions. It's smooth, it's flexible, and it extends infinitely. Now place a bowling ball in the center of that sheet. The ball doesn't push down on the sheet with some mysterious force. Instead, its mass warps the very fabric of spacetime around it. The sheet curves and bends. It develops a depression, a valley around the ball. Now, when you roll a marble across that curved sheet, it doesn't travel in a straight line like it would on a flat surface. It curves toward the bowling ball, following the contours of the warped spacetime. That curved path is what we perceive as gravity. The marble isn't being pulled by an invisible force. It's following the geometry of the space it's moving through. This insight was revolutionary. Gravity wasn't action at a distance anymore. It wasn't some mysterious force propagating through empty space. It was the geometry of the universe itself responding to the presence of mass and energy. And the mathematics was so elegant, so powerful, so beautiful that it made predictions Newton's theory never could. It explained the precession of Mercury's orbit with perfect accuracy. Newton's theory said Mercury should orbit the Sun in a perfect ellipse, but Mercury's orbit actually precesses. The perihelion, the point of closest approach to the Sun, shifts slightly with each orbit. Einstein's equations explained this shift exactly, predicted that light would bend around massive objects. This was counterintuitive. Light was supposed to be massless. How could a massless thing be affected by gravity? But Einstein's equations said that gravity bends spacetime, and light follows the curves of spacetime. So light should bend around massive objects. When Arthur Eddington observed a solar eclipse in 1919, he positioned telescopes to photograph stars near the Sun's edge. According to Einstein's predictions, the Sun's gravity should bend the starlight, making the stars appear to shift from their normal positions. When Eddington analyzed the photographs, he found exactly this shift. The starlight had bent around the Sun just as Einstein predicted. In one moment, Einstein went from being a brilliant but relatively unknown theoretical physicist to being a world-famous figure. The headline in the Times of London read something like, "Revolution in Science, New Theory of the Universe." And it was true. Einstein had revolutionized our understanding of gravity and spacetime. But here's where things get really interesting, and where I want you to pay close attention, because this is where gravity starts to reveal cracks in the foundation of physics. This is where gravity begins to threaten to break the universe. In the 1960s and 1970s, a brilliant physicist named Stephen Hawking made a discovery that seemed impossible. He combined Einstein's gravity with quantum mechanics, and what emerged was something that shattered our understanding of black holes forever. Black holes, Einstein's theory predicted, should be completely black. Once something crosses the event horizon, the point of no return, nothing can escape, not even light. But Hawking showed that black holes are not completely black. They emit radiation. They have a temperature, they have entropy, and remarkably, they can evaporate completely. This Hawking radiation, as it came to be known, was the first significant hint that gravity and quantum mechanics are fundamentally incompatible at the deepest levels. Here's why. Quantum mechanics says that at the smallest scales, at the Planck scale, about 10 to the minus 35 meters, which is almost incomprehensibly small, reality becomes probabilistic. Particles don't have definite positions and momenta. They exist in a cloud of probability. They can be in superposition in multiple states at once until measured. But Einstein's gravity, his general relativity, describes a smooth, continuous spacetime. These two pillars of modern physics tell completely different stories about how reality works. At the event horizon of a black hole, where gravity becomes infinitely strong, quantum effects become crucially important, and these two theories collide head-on. Something has to give. Scientists have been trying for decades, centuries really if you count from Newton onward, to reconcile these two incompatible theories. Some propose string theory, which suggests that fundamental particles aren't points but tiny vibrating strings. Others suggest loop quantum gravity, where spacetime itself is quantized into discrete loops. Still others propose that spacetime is an illusion, emerging from something more fundamental, perhaps from pure information, perhaps from quantum entanglement, perhaps from something we haven't even conceived of yet. But here's the thing, we don't know which, if any, of these approaches is correct. And that's the first hint that gravity might allow us to break the universe, by revealing the deepest contradictions in our understanding of nature. But wait, there's more. Much more. In 1998, astronomers Saul Perlmutter, Brian Schmidt, and Adam Rees made an observation that completely blindsided the physics community. They were studying type Ia supernovae, these brilliant cosmic explosions that occur when a white dwarf star, the remnant of a sun-like star, pulls material from a companion star. Type Ia supernovae have a peculiar property. They have roughly the same intrinsic brightness, the same absolute magnitude. This makes them excellent standard candles for measuring cosmic distances. If you know how bright something actually is intrinsically, and you measure how bright it appears from Earth, you can calculate how far away it is. So Perlmutter, Schmidt, and Rees measured the distances to dozens of these supernovae, going back billions of years into cosmic history. Using telescopes to observe incredibly distant galaxies, they measured the light from supernovae that exploded billions of years ago. And here's what they expected to find. The universe is expanding. We know that from Hubble's observations a century earlier, but they expected the expansion to be slowing down. Gravity, after all, is attractive. The gravitational pull of all the matter in the universe, all the stars, all the planets, all the gas, all the dark matter, should be pulling things back together. It should be decelerating the cosmic expansion. The universe should be expanding, but slowing down over time, like a ball thrown upward against gravity. But that's not what they found. The supernovae were farther away than they expected. The universe wasn't just expanding, it was accelerating. The expansion was speeding up. It was as if someone had pressed the cosmic gas pedal. The universe was expanding faster and faster. This was so shocking that when these results were first presented, many physicists thought there must be a mistake. There had to be systematic errors in the observations. There had to be dust blocking their view. There had to be something they hadn't accounted for. But the results held up. The observations were repeated. Different teams confirmed the findings. The evidence became overwhelming. The universe is accelerating, and that means something is pushing the galaxies apart with an ever-increasing force. Something is working against gravity. Something is causing the cosmic expansion to speed up, and we have absolutely no idea what it is. We call this mysterious force dark energy, and it comprises about 68% of the entire universe. 68%. Think about that for a moment. Let that sink in. Everything you can see, every star, every galaxy, every supernova, every comet, every asteroid, every planet, every speck of dust, even you, all of that makes up only 32% of the universe's total energy content. The visible universe, everything that emits light or reflects light, everything made of atoms like the ones in your body, comprises only about 5% of the universe. The vast majority of matter is dark. We can't see it, we can't touch it, we can't observe it directly. We only know it exists because of its gravitational effects. And then there's dark energy, which comprises 68% of everything. We're rounding errors in the cosmic budget. We're like a drop of water in an ocean that is itself immeasurably vaster than we can conceive. The universe is driven primarily by something we don't comprehend. We don't know what it is. We don't know where it comes from. We don't know if it's constant or if it varies over time. And this should terrify and humble every physicist on Earth. We've built a magnificent edifice of understanding about gravity and the universe, and it turns out we're missing the dominant component. Now, dark energy presents a fundamental problem to gravity as we understand it. Einstein's equations relate the geometry of spacetime to the distribution of matter and energy. If you know where the matter and energy are, you can solve Einstein's equations and find the curvature of spacetime. If you know the curvature of spacetime, you can predict how objects will move. But dark energy is smooth. It's not concentrated in galaxies or clusters of galaxies. It's distributed uniformly throughout space. And it has a really weird property. Its energy density doesn't change as the universe expands. Let me say that again because it's important. In normal physics, when something expands, it gets diluted. If you have a gas in a container and you expand the container, the density of the gas goes down. But dark energy doesn't work that way. As the universe expands and becomes larger, dark energy doesn't get diluted. In fact, it seems to get more powerful. The expansion accelerates faster and faster. This shouldn't be possible. but that's what we observe. Some physicists propose that dark energy is simply the cosmological constant, a fudge factor that Einstein himself had introduced into his equations back in 1917, then later called his greatest blunder. The cosmological constant is just a form of energy inherent to spacetime itself, present everywhere and forever, unchanging throughout the history of the universe. But this creates an enormous problem called the cosmological constant problem, one of the biggest unsolved mysteries in physics. It's so fundamental, so troubling, that it might be the key to unlocking a whole new level of physics. Quantum field theory, when applied to the vacuum, empty space, predicts that the vacuum should have enormous energy density. The calculations suggest it should be about 10 to the 120 power times larger than what we actually observe. That's 1 followed by 120 zeros. To give you a sense of scale, there are only about 10 to the 80 atoms in the observable universe. There are more zeros in the predicted vacuum energy than there are atoms in the entire universe. It's not like being off by a little bit. It's not being off by a factor of 1,000 or a million or a billion. It's off by 10 to the 120. It's the most catastrophic disagreement between theory and observation in the entire history of science. It's so bad that physicists have mostly stopped talking about it in public because it makes us sound crazy. But privately, it haunts them. It haunts me. This discrepancy suggests that either quantum field theory is fundamentally wrong at some level, or general relativity breaks down at the scales we're probing, or both are incomplete, or something entirely different is going on that we haven't even conceived of yet. And this is the second way gravity threatens to break the universe, by revealing fundamental contradictions at the largest scales. The universe is not just a bigger version of what we've tested in laboratories and with satellites. It operates by rules we don't yet understand. Let me take you even deeper into this mystery. Let's go back to the smallest scales, because there's another profound mystery brewing there that could transform everything we know. In recent years, physicists have become increasingly interested in what happens at the singularities of black holes. The singularity is that point of infinite density at the center of a black hole, where all the matter has been compressed to an infinitely small volume, where the curvature of spacetime becomes infinite. It's where general relativity breaks down completely. The equations blow up. You get infinities everywhere. And infinities in physics are usually a sign that you're pushing your theory beyond its domain of validity. It's like trying to use Newton's laws to describe the collision of two particles at the speed of light. The equations don't work. They give nonsensical answers. Now, according to Einstein's theory, once you cross the event horizon of a black hole, you're doomed. Your fate is sealed. Nothing can escape. Not even light. Not even you. Time and space swap roles inside the event horizon. You can move toward the future, and the future points toward the singularity. You can no longer escape the singularity any more than you can escape tomorrow. Your inevitable future is the singularity. But if gravity, as Einstein described it, is all there is, then that singularity is a real physical thing. It's a place where our physics completely fails. It's a place where the universe breaks. But what if gravity doesn't have the final word? What if, at the smallest scales, at the Planck scale, quantum effects become so important that they dominate? What if, as you approach the singularity, quantum gravity effects become so strong that they prevent the singularity from ever forming? This is speculative, absolutely speculative, but some physicists have proposed models where black holes don't actually contain true singularities. Instead, quantum effects might create a firewall, a region of incredibly intense energy at the event horizon. Or perhaps quantum gravity effects create a bounce at a Planck scale radius, bouncing matter back outward before it can form a singularity. Or perhaps the black hole evaporates via Hawking radiation without ever developing a true singularity. If this is true, if quantum gravity naturally prevents singularities from forming, then it means that gravity, combined with quantum mechanics, naturally prevents the universe from breaking, prevents infinities from appearing. It prevents the mathematical structure of spacetime from developing true singularities. It regularizes itself. That's beautiful. That's elegant. That's what we'd hope to find in a truly fundamental theory. But it also means we need a theory of quantum gravity to understand black holes properly. And we don't have one yet. Now, let's talk about something that really keeps me awake at night. the possibility that gravity itself might be emergent, that spacetime and gravity might not be fundamental at all. Over the past 2 decades, a growing number of physicists have entertained a radical idea. And when I say radical, I mean it challenges the very foundation of how we think about physics. What if spacetime and gravity are not fundamental? What if they emerge from something more basic, something we haven't discovered yet? This isn't the ravings of pseudoscientists. This is being explored by serious physicists at serious institutions. This idea is inspired, in part, by the ADS/CFT correspondence discovered by Juan Meldacena in 1997. ADS stands for anti-de Sitter space, a particular type of curved spacetime. CFT stands for conformal field theory, a quantum field theory without gravity. Meldacena discovered something astonishing. A gravitational theory in anti-de Sitter space is mathematically equivalent to a quantum field theory in a lower-dimensional space without gravity. It's like a hologram. The 3-dimensional gravitational theory is like a hologram of the 2-dimensional quantum field theory. All the information in the gravitational theory is encoded in the lower-dimensional field theory. This correspondence is not just a mathematical curiosity. It suggests that gravity might be emergent. It suggests that if you have the right quantum field theory living on the boundary of spacetime, gravity emerges in the bulk. It's like the way temperature emerges from the motion of molecules. Individual molecules don't have temperature. But when you have trillions of molecules moving around, bouncing off each other, you can define a temperature that describes the average kinetic energy. Similarly, gravity might emerge from quantum information or quantum entanglement. If gravity is emergent, it means that all the weird things we associate with gravity, black holes, singularities, event horizons, curved spacetime, might not be fundamental aspects of reality. They might be collective phenomena. They might arise from something at a deeper level that we haven't yet discovered. This is like understanding fluid dynamics. Fluid dynamics seems to be a fundamental description of how liquids and gases behave. Water flows, air currents swirl, things float and sink. But at a deeper level, fluid dynamics emerges from the motions of zillions of individual molecules. Individual molecules don't flow. They bounce around randomly, but collectively, they create the phenomenon we call fluid flow. Similarly, gravity might emerge from something at a deeper level. Spacetime might not be fundamental. It might be an emergent phenomenon. And that would mean our understanding of gravity is like our understanding of temperature before we knew about atoms. We knew temperature was real. We could measure it. It was incredibly useful. But we didn't understand it was really just the average kinetic energy of zillions of particles. We thought it was a fundamental property of matter. But it wasn't. Similarly, gravity might be real and useful and predictive, but it might ultimately be a statistical phenomenon arising from something far more fundamental. This is speculative, absolutely, but if it's true, it has profound implications. It suggests that the next revolution in physics won't be modifying Einstein's equations. It will be realizing that Einstein's equations are an effective description of something deeper, and that's a completely different kind of revolution. Let me introduce you to another mystery that connects gravity to the very fabric of existence: the nature of time itself. In Einstein's relativity, time is not absolute. It's not the same everywhere. It's relative. It flows at different rates depending on gravity and velocity. This is not just theoretical speculation. We've measured it. We've tested it. Atomic clocks on airplanes tick at slightly different rates than atomic clocks on the ground due to the speed of the airplane. More dramatically, atomic clocks on satellites tick at different rates than atomic clocks on the surface of the Earth. GPS satellites wouldn't work without relativistic corrections. If you didn't account for the fact that time runs faster in space, farther from the Earth's gravity well, than it does on the surface of the Earth, GPS would give you your location wrong by kilometers within hours. Time actually runs faster in space because gravity is weaker there. And near black holes, time slows to a crawl. At the event horizon of a black hole, time stands still. An external observer would see an infalling object asymptotically approach the event horizon, moving slower and slower, its light becoming more and more redshifted, until it seems to freeze at the horizon. But to the infalling object, it would cross the event horizon in finite time and hit the singularity. But here's where it gets really strange and really problematic. Physics at the quantum level operates in a very different way. In quantum mechanics, there's a fundamental symmetry called time reversal symmetry. Many quantum processes look the same whether time flows forward or backward. If you recorded a quantum interaction at the atomic scale and played it backward, you wouldn't be able to tell the difference. It would look just as valid. But gravity breaks this symmetry spectacularly. The universe evolves in one direction through time. Entropy increases. We age. We move from the past to the future. Stars. Black holes form. Galaxies collide. These processes are fundamentally asymmetric in time. You don't see stars unburning. You don't see black holes unforming. You don't see galaxies uncolliding. This asymmetry is called the arrow of time. Now, here's the mystery that keeps physicists up at night. Where does this arrow come from? What in the laws of physics creates the distinction between past and future? The microscopic laws, both quantum mechanical and gravitational, are largely time reversible. But our macroscopic experience is not. The universe evolves from low entropy to high entropy, from order to disorder, from structure to chaos, and nobody really understands why. Some physicists argue that it has to do with the initial conditions of the Big Bang, which was in an extraordinarily low entropy state. The Big Bang started in a very ordered, structured state. As time went on, entropy increased, disorder increased. But why was the Big Bang in such a low entropy state? Why didn't it start in maximum entropy? Why was it special? And what role does gravity play in that? This is profound because it suggests that the arrow of time might be connected to gravity. The initial low entropy of the Big Bang might have been determined by gravity somehow. The evolution of the universe under gravity might naturally increase entropy. And that would mean gravity is not just the geometry of spacetime. It's also the arrow of time. Roger Penrose, one of the greatest living physicists, has proposed that this time asymmetry might be fundamental to how gravity works. He's suggested that gravity, over cosmological timescales, actually drives the universe toward ever-increasing entropy. And he's proposed a model called conformal cyclic cosmology, or CCC, where the universe goes through infinite cycles, each one being the infinite future of the previous one. In each cycle, gravity is so strong and spacetime becomes so vast that the very distinction between the infinite future and a new beginning becomes meaningless. The infinite past of one universe is identical to the infinite future of another. Time is cyclical, but at a scale so vast that within each cycle it appears linear. If Penrose is right, if his conformal cyclic cosmology is the true description of the universe, then gravity is not just responsible for orbits and tides. It's not just the geometry of spacetime. It's responsible for the fundamental direction of time itself. It's responsible for the distinction between past and future. And that would mean gravity is even more fundamental, even more central to existence than we've ever imagined. It would mean that the nature of time, your experience of moving from past to future, your memories of the past, your hopes for the future, is ultimately a consequence of gravity's influence on the structure of spacetime. It would mean that without gravity, there would be no time. There would be no before and after. There would be no change. Now, let's consider one more mystery that brings all of these threads together: the black hole information paradox. In the 1970s, Stephen Hawking made that astonishing discovery that black holes emit radiation. And from that radiation spectrum, you can extract the temperature of the black hole, which is related to its mass. The smaller the black hole, the hotter it is. And the hotter something is, the faster it radiates energy. This means smaller black holes evaporate faster. Eventually, any black hole will evaporate completely, in a process that could take longer than the current age of the universe, 10 billion years for stellar mass black holes. But for tiny black holes, it could happen in microseconds. But here's the problem, and it's a deep one that cuts right to the heart of the incompatibility between gravity and quantum mechanics. When a black hole evaporates via Hawking radiation, where does all the information that fell into the black hole go? Quantum mechanics, one of the pillars of modern physics, says information can't be destroyed. It has to go somewhere. It has to be encoded in the pattern of the radiation that emerges. But when you do the calculations, you find that the Hawking radiation is completely thermal. It's random. It has no information encoded in it. Every black hole that forms from the same initial conditions and evaporates will produce essentially the same radiation. There's no way to distinguish them. There's no way to recover the information about what fell in. If you throw a book into a black hole, that book, all the information in it, seems to be lost forever. If you throw a different book into an identical black hole, it would evaporate and produce indistinguishable radiation. This violates the fundamental principle of quantum mechanics that information is conserved. This is the black hole information paradox, and it's a direct contradiction between gravity and quantum mechanics. Einstein's general relativity says that information can be lost in a black hole. Quantum mechanics says it can't. Both can't be right. Something has to give. And resolving this paradox might require a completely new understanding of gravity. Some physicists, like Juan Meldacena and others, have argued that the information isn't really lost. It's scrambled. It's in the radiation, but in such a way that it's impossible to extract with any practical measurement. The information is there, but it's so thoroughly mixed up that you'd need to analyze the Hawking radiation in impossible ways to extract it. Others argue that gravity must be modified near black holes to prevent the information loss. Perhaps gravity becomes stronger or weaker near the singularity in a way that allows information to escape. And some argue that the paradox is telling us that gravity, at the most fundamental level, is not a continuous field but something more discrete and quantum in nature. The resolution of this paradox could fundamentally reshape our understanding of gravity. It could reveal that gravity at the Planck scale is quantized like all other forces. It could show that spacetime has a discrete structure, like a lattice of quantum events. It could reveal that spacetime is not continuous but made up of discrete chunks. Or it could reveal something we haven't even thought of yet. Now, I want to step back and talk about what all of these mysteries mean for the future of physics. Because I think we're at a turning point. We're at a crucial moment in human history where our understanding of the universe is about to undergo a fundamental transformation. Gravity is the only fundamental force we haven't successfully quantized. Electromagnetism, the weak nuclear force, and the strong nuclear force have all been incorporated into quantum field theories. We understand these forces at both quantum scales and large scales. But gravity has resisted every attempt. And I don't think that's an accident. I think it's telling us something profound. There are several possibilities for what that something might be. First, gravity might be fundamentally different from the other forces. Maybe quantizing it requires a completely different approach than what worked for the other forces. The weak and strong nuclear forces, electromagnetic force, they all operate in the framework of quantum field theory. They're all mediated by particles. But gravity doesn't fit nicely into this framework. Maybe we need a new framework entirely. Second, maybe spacetime itself is not the right framework. Maybe the very concept of spacetime, a four-dimensional continuum with 3 spatial dimensions and 1 temporal dimension, is not fundamental. Maybe it's an approximation. Maybe at the deepest level, reality is not a spacetime at all. Maybe it's something else. Maybe it's information. Maybe it's patterns of quantum entanglement. Maybe it's pure mathematics. But whatever it is, it's not spacetime. Third, maybe there are additional dimensions that we don't know about. String theory predicts 10 or 11 dimensions, depending on the version. Maybe we live in a world with many more dimensions than we perceive. Maybe gravity is actually strong in those extra dimensions, and what we perceive as the weakness of gravity on large scales, the fact that gravity is so much weaker than the other forces, is because it's spreading into dimensions we can't see. Most of the gravitational force is in the extra dimensions. What we see is just the spillover. Fourth, maybe gravity is an illusion. Maybe it's not even a real force. Maybe it's an emergent phenomenon arising from something at a deeper level, like the entanglement of quantum information. This last possibility sounds crazy, but serious physicists are exploring it. It's called entropic gravity, the idea that gravity is not fundamental but is a consequence of entropy maximization in quantum systems. The universe, in a sense, tries to maximize entropy, and gravity emerges as the manifestation of this principle. Fifth, maybe time itself is not fundamental. Maybe the past, present, and future all exist equally. Maybe time is like space, you can move backward in space, and in the same way, The universe exists in a static, unchanging block where past, present, and future all coexist. This is called block universe or eternalism, and it's a serious position in philosophy of physics. If time is not fundamental, if all times exist equally, then the evolution of the universe is also not fundamental. It's just the structure of the four-dimensional spacetime. Any of these possibilities would represent a revolution in physics. And I suspect that understanding how to resolve the contradictions within gravity, how to reconcile it with quantum mechanics, how to explain dark energy, how to resolve black hole information paradoxes, how to understand time, will require embracing one or more of these radical ideas. But here's what I find most fascinating. These mysteries of gravity might be the gateway to understanding something even deeper about the nature of existence itself. Let me explain what I mean. In recent decades, physicists have become increasingly interested in the role of quantum entanglement in the structure of spacetime. Entanglement is that phenomenon Einstein called spooky action at a distance, where two quantum particles can be correlated in such a way that measuring one instantly affects the state of the other, no matter how far apart they are. It's real. We've tested it extensively. It's been confirmed over and over. And it's one of the most counterintuitive features of quantum mechanics. When two particles are entangled, they share a quantum state. They're connected in a fundamental way. And what's remarkable is that this connection is not mediated by any signal traveling between them. It's instantaneous. It's as if the particles are part of a single quantum system, no matter how far apart they are. This seems to violate relativity, which says nothing travels faster than light. But it doesn't actually violate relativity because you can't use entanglement to send information faster than light. The correlations only become apparent after you communicate the measurement results, which travels at or below the speed of light. Now, some physicists, including those working on the ADS/CFT correspondence and related holographic theories, have begun to suspect that entanglement is not just a quantum phenomenon. It might actually be responsible for creating spacetime itself. The idea is that spacetime emerges from a web of entangled quantum information. Imagine a vast network of qubits, the quantum equivalent of bits. These qubits are entangled in a complex pattern. The pattern of entanglement determines the structure of spacetime. Regions that are highly entangled are close together in spacetime. Regions that are weakly entangled or not entangled are far apart. If two regions become disentangled, spacetime develops structures that separate them. Wormholes form, boundaries appear. As the universe evolves, as interactions occur between qubits, the pattern of entanglement changes. With it, the geometry of spacetime itself changes. Stars form, galaxies form, black holes form, universes might even split. If this is true, and this is still highly speculative, it's on the frontier of theoretical physics, then gravity is not a force at all. It's the geometry of spacetime, which emerges from the pattern of entanglement in the quantum state of the universe. This would mean that understanding gravity at the deepest level requires understanding how entanglement gives rise to spacetime. It would mean that gravity and entanglement are two faces of the same phenomenon. And that would represent a complete unification of quantum mechanics and gravity, but at the cost of completely reconceiving both. This is where I think physics is headed. Not toward a modification of general relativity or quantum mechanics, but toward something deeper that encompasses both. A theory where spacetime, gravity, and quantum entanglement are all understood as different aspects of the same underlying reality. A theory where what we call gravity is really the structure of a vast network of entangled quantum information. Where what we call spacetime is the geometrical manifestation of quantum correlations. Now, let's talk about the implications of these ideas for actually breaking the universe, as your title suggests. What does it mean to break the universe? I think it means to discover something that violates the fundamental laws of physics as we understand them. It means to find the limit of our understanding and push beyond it. It means to realize that our current framework is incomplete or incorrect. And I believe that gravity is the key to doing that. Gravity is the wall we've hit. It's the place where our understanding breaks. And breaking through that wall might lead to a completely new understanding of reality. First, understanding gravity properly will likely resolve the contradiction between quantum mechanics and general relativity. This alone would be earth-shaking. It would give us a unified theory of all the forces and all of physics. We've already unified electromagnetism and the weak nuclear force into electroweak theory. The strong nuclear force is described by quantum chromodynamics. But gravity stands apart. It's the odd one out. If we could incorporate gravity into a quantum framework, or if we could understand how quantum mechanics emerges from gravity, we would have a unified theory of everything. We would have a framework that describes all the forces, all the particles, all the phenomena we observe, from the smallest subatomic scales to the largest cosmological scales. That's profound. But more than that, it would mean we understand the deepest level of reality. We would have a theory of quantum gravity that explains what happens at black hole singularities, what happens at the moment of the Big Bang, when gravity was infinitely strong and the universe was infinitely hot. We would understand the origin of the universe itself. Or perhaps we would realize that the universe doesn't have an origin in the conventional sense. Perhaps it's eternal. Perhaps it's cyclical. But whatever it is, we would understand it. Second, understanding gravity might explain dark energy. Maybe dark energy is not a mysterious form of energy at all. Maybe it's a sign that gravity behaves differently at cosmological scales. Maybe Einstein's equations need to be modified. Maybe gravity becomes repulsive on the largest scales. Or maybe gravity is weaker than we think on those scales, and what we interpret as dark energy is actually a sign that Einstein's theory breaks down for cosmological geometry. There are alternative theories of gravity that attempt to explain cosmic acceleration without dark energy. They modify general relativity slightly, adding extra terms to Einstein's equations that become significant at large scales. These modified gravity theories make different predictions for structure formation and the growth of galaxies, and we're testing them against observations. If we can explain dark energy, we'll have explained 68% of the universe. That's enormous. We'll have solved one of the deepest mysteries of cosmology. Third, understanding gravity might reveal whether the universe is eternal or whether it had a beginning. And if it had a beginning, it might tell us what came before, which sounds nonsensical until you realize that gravity, according to some theories, creates time itself. Stephen Hawking and others have proposed that the universe might be self-contained in spacetime. The boundary of spacetime is at the Big Bang, which is at infinite density and infinite temperature. But in quantum gravity, you're supposed to integrate over all possible spacetimes, not just classical spacetimes. Hawking proposed that quantum gravity naturally selects spacetimes without boundaries. And spacetime without a boundary means there's no singularity. There's no moment of creation. The universe just is. It always was. If this is true, asking what came before the Big Bang is like asking what's north of the North Pole. It's a meaningless question. There is no before. Time itself begins at the Big Bang. But understanding why it's meaningless, understanding the quantum gravity principles that lead to a no-boundary universe would be profound. It would reshape our understanding of existence itself. Fourth, understanding gravity might transform our understanding of consciousness and the nature of mind. This sounds even more far-fetched, and I want to be careful here because this is deeply speculative. But some physicists and philosophers have speculated about the connection between the collapse of quantum wave functions, when a superposition of possibilities becomes a definite reality, and the moment of conscious observation. If consciousness is somehow involved in quantum collapse, and if gravity influences quantum behavior, then gravity might be connected to consciousness. Now, most physicists would dismiss this outright. The hard problem of consciousness, why and how physical processes give rise to subjective experience, is a notoriously difficult philosophical problem. And connecting it to gravity seems like a stretch. But a few serious researchers, including some Nobel laureates like Penrose, have thought deeply about this. And they've proposed models where quantum effects in the brain, particularly in microtubules within neurons, might be relevant to consciousness. Penrose has proposed that quantum gravity effects in the brain might be responsible for consciousness. That consciousness is a quantum gravity phenomenon. This is deeply speculative. I want to emphasize that we don't have evidence that consciousness is connected to gravity. But understanding gravity might shed light on this mystery too. It might force us to revise our understanding of consciousness. But perhaps most fundamentally, Understanding gravity means understanding the nature of reality itself. Because gravity, Einstein taught us, is not a force that exists in spacetime. Gravity is the structure of spacetime. To understand gravity is to understand the fabric from which all of existence is woven. It's to answer the question, what is space? What is time? Why does space have 3 dimensions and not 4 or 2? Why does time flow in one direction? Why does the universe have the properties it has? These are the deepest questions in physics and philosophy, and gravity is the key to answering them. Now, I want to be clear about something. We might never fully resolve all these mysteries. Physics has always been about pushing back the frontiers of the unknown, but there are always new frontiers beyond. As we solve problems, we discover new ones. The history of physics is not a march toward a final theory. It's a spiral. We get closer and closer to understanding, but the deeper we dig, the more we realize how much deeper the mystery goes. And I think this is how it will always be. We'll make progress. We'll understand more. But the universe will always have secrets. But that's not a failure of physics. That's what makes it beautiful. That's what makes it alive. That's what makes it worth doing. Every time we understand something, the universe opens up new doors of mystery. We solve one puzzle and discover 3 new ones. And gravity is the deepest mystery of all, because it's the structure of existence itself. Let me conclude with something that I think connects all of these threads and points toward where the physics of the future might lead us. We live in a universe that is fundamentally mysterious. We understand some things. We understand electromagnetic interactions. We understand how light works. We understand how atoms bond together. We understand the weak nuclear force which is responsible for radioactive decay. We understand the strong nuclear force which holds nuclei together. We've gathered these understandings together in what we call the standard model of particle physics. It's remarkably successful. In many domains, it makes predictions accurate to better than 1 part in a billion. It's one of the most successful theories in the history of science. But gravity sits apart from this framework. When you try to apply quantum field theory techniques to gravity, you get infinities. You get nonsensical answers. The theory breaks down. And I think that's not an accident. I think it's telling us that gravity is the key that unlocks the next level of understanding. Gravity is pointing the way forward. When we finally understand gravity, when we figure out how to reconcile it with quantum mechanics, when we explain dark energy, when we resolve the information paradox, when we understand the nature of time, I believe we'll discover that the universe is even stranger, even more wonderful, and even more connected than we currently imagine. We might discover that spacetime is not fundamental but emergent. We might find that the universe is infinite dimensional, or that it has some other structure we haven't conceived of. We might learn that quantum entanglement, which seems so spooky and distant from gravity, is actually the mechanism that creates spacetime itself. Entanglement might be the fundamental reality, and spacetime might be derivative. We might discover that what we call the laws of physics are not laws at all, but regularities that emerge from something more fundamental. Perhaps from pure mathematics, perhaps from quantum information, perhaps from something we don't have a name for yet. And in the process of understanding gravity, we might break down the last barriers that prevent us from saying we truly understand the universe. Not in the sense of understanding every detail. That's impossible. The universe is too vast, too complex. Every time we explain one thing, we discover that it depends on something else. That's the nature of science. But we could arrive at understanding the deep principles, the fundamental architecture, the basic rules from which everything else emerges. That's the promise of understanding gravity. That's what it means to allow gravity to break the universe in the sense of breaking through to a new level of understanding. And that's what I find absolutely breathtaking about the future of physics. Because here's the thing, you are made of atoms forged in the cores of stars. Those atoms exist because of gravity. Those stars collapsed under gravity. They burned because gravity maintained the pressures and temperatures in their cores, allowing nuclear fusion to occur. And even now, you're being pulled toward the center of the Earth by gravitational force. Gravity created you, gravity sustains you, and gravity will eventually reclaim you when you return to dust. And yet, Despite the fact that gravity has shaped your existence at every moment of your life, we don't truly understand what it is. That's humbling. It's also inspiring, because it means that one of the great unsolved mysteries of science, one of the deepest questions about the nature of reality, remains open. It means that there's still frontier territory. There's still something to discover. There's still mystery left in the universe. And somewhere, right now, a physicist or a mathematician or someone we haven't discovered yet might be working on the insight that transforms everything. That insight might come from a completely unexpected direction. It might require thinking about gravity in a way nobody has thought about it before. It might come from combining ideas from quantum information theory with ideas from cosmology. It might come from a child doodling in a notebook. But when we finally solve the mystery of gravity, the universe will never look the same again. This is COSM Hush, and this has been our exploration of the main mystery of gravity. How it might allow us to break the universe, to transcend our current understanding and reach toward a deeper truth about existence itself. We've explored Newton's gravity and Einstein's revolution. We've confronted the contradiction between quantum mechanics and general relativity. We've grappled with dark energy and the cosmological constant problem. We've considered black hole information paradoxes. We've imagined spacetime emerging from quantum entanglement. We've asked fundamental questions about time and the arrow of time. And we've glimpsed the possibility that gravity might be emergent, not fundamental. The journey continues. The mystery deepens. And the greatest discoveries in physics are probably still ahead of us. They're waiting to be found by the next generation of physicists, the next generation of scientists, the next generation of curious humans who look up at the night sky and wonder about the nature of existence. Thank you for joining me on this cosmic journey. Thank you for thinking deeply about these profound mysteries. Thank you for wondering, because that's what makes us human. That's what makes us scientists. That's what drives us forward. Keep looking up, keep wondering, and keep questioning everything, because that's the spirit that has driven human understanding forward. And it's the spirit that will eventually solve the greatest mysteries of all.